phone call came in. And it breaks my video when that happens. I was going and I turn around and it's like, oh, it's a spam call. Thank you, spam, for doing that to me. I think we were at the point where I was saying that the ice melts and becomes water, and we go through a phase change, and we get no temperature change during a phase change, and that's muy importante grande to remember. And so all the energy goes into breaking bonds. Bond, I must break you. No, I am a Majesty's Secret Service agent. You will never break me. Yes, we must break you, Bond. Okay, that's what's going on here. We have to break the bonds. We have to crush the crystal structure. Now, I was redrawing this when I realized the video was off, that I took the 0 and moved it over here and put an ice cube here, because it's still going to be ice. At 0 degrees, we get cold ice, and we get warm ice, if that makes any sense, like an oxymoron there. So cold ice, warm ice at 0, then it melts and becomes water at 0. The water is immediately at cold 0 degree temperature, and then what happens to the water? Well, we're cranking the heat into it right at this point because we want to vaporize it, so it gets warmer. And it goes up to become water at 100 degrees. And then when it's water at 100 degrees, then what happens to it? Then, get this a little bit smaller, phase change, and then it becomes vapor. I'll make my vapor little circles like that, little water vapor. And that's water vapor at 100 degrees Celsius. Okay, so that's what's happening. Look at this picture. It has 1, 2, 3, 4 arrows on it. That's important, because for each arrow, we have to do a calculation, okay? Just a minute, hang on. Okay, now, so we get a, and up here too, look, during a phase change, we're going from boiling, we're boiling the water, going from liquid to a solid, liquid to a gas. During that boiling phase, we have a flat line, no temperature change. We get all the energy going to breaking those hydrogen bonds. Remember, they don't want to break, no! And so we have to pump energy in to cause those water molecules to separate and form vapor. Okay, and you know this is true. You know there's no phase, during a phase change, there's no temperature change. You know that. Yes, you do. Think about this. Let's say that you should, and if you haven't done this, you should do it right now. Get a nice big pile of water, pot of water, put it on the stove and boil it. Just boil it, just let it boil. It's good entertainment, watch it, it's fun. Then take a thermometer, put a thermometer in the boiling water. What's it going to read? Well, considering we're near sea level here in central New Hampshire, it's going to be about 100 degrees Celsius. Of course, boiling temperature does change as you go up in elevation, it goes down. But it's going to be 100 degrees. So 100 degrees, you read that. Then go out, take a walk. Walk down the street like this. You know, like you're in West Side Story. That's how they walk. Cool. Okay, walk down the street. And you might not want to do that. You probably get beat up or something. But anyway, do that for 5 minutes, come back. Put the thermometer in again, read the temperature. What's it going to read? You know, 100 degrees. The temperature doesn't go up while you're boiling the water. It stays at 100. The temperature doesn't go up while you're boiling the water. It stays at 100. So you know during a phase change, you get no temperature change. Okay, so now what we want to do is figure out the amount of energy, the amount of heat energy it takes to do this process. This is a 4-step problem, people, 4-step problem. Each arrow represents a step. This is step 1, this is step 2, this is step 3, and this is step 4. You have to treat each step individually. You cannot combine them. It's a 4-step problem no matter how you slice it. Okay, all right, okay, now what do I do? Okay, all right. I'm going to pull from Chem 1 an equation that you had. Yes, you did, you had this. I call it the heat equation. For step 1, we're going to need Q is equal to M delta T Cp. All right, this is mass, delta change in temperature, Cp is specific heat capacity. All right, the Pacific heat capacity, not the Atlantic heat capacity. It's an ocean joke. It's not Pacific either. It's specific heat capacity. It was funny, though. It was funny, right? It was funny. Now, some of you might remember this as MCAT. M, and you switch these, C, and the delta looks like an A, T, so cat. It doesn't make any difference what order you do it in, you're multiplying them, so whatever. This is the heat equation. It works for step 1 because we have a mass, this is 1 kilogram. We have a change in temperature, okay, the temperature's going up, and we have a specific heat for ice that we'll have to put in there. Be careful, we don't need, it's not water yet, it's ice here, so we need Cp of ice. Here we don't have a temperature change. We cannot use this equation. This needs a temperature change. If there's no temperature change here, there's energy going into the system to break bonds, but we're not changing temperature. Will not work. We need a different thing. Hang on. Step 3, we can use that again because we have a temperature change. Let's write that down. So Q is M delta T CP. That will work for step 3. Step 4, the heat equation will not work. We don't have a temperature change. So we need 2 other equations. Here they are. This first step. Okay. And you can go ahead and look at the equation sheet. It's in Essential Documents. I put an equation sheet 1. There's your equations, and these equations are on there. And here is one of those off the equation sheet. Q, heat to melt, fuse. So Q sub F equals, oh, this one here is not Q, heat H F times M. Now this means the heat that's going to take to melt the ice is going to be equal to the heat of fusion for that ice multiplied by the mass of the ice. Now, of course, if this is not ice, it's something else. It's like doing the heat of fusion for steel or for copper, and I want to melt copper. Well, then I wouldn't use the heat of fusion for water. I would use that for copper, and I'd have to look up and see what that is. But we're doing water. Okay. Here, the Q, heat to vaporize V, equals HV, heat of vaporization, multiplied by M. That's 100 degrees. Okay, those are my equations. Now, some of you might be saying, hey, well, can't we combine this one here and this one here? Because it's the same equation, just combine them. Save us a step. No, for 2 reasons you can't do that. 1, the temperature change here is much different than the temperature change here. And 2, the specific heat capacity for ice is different than the specific heat capacity for water. Yeah, can't combine them. You have to do 4 steps. Let's get started. Let's do those 4 steps. Okay, be organized. Step 1. I'm going to do it right down here. So the Q is equal to the mass. What was the mass? 1 kilogram. Now I'm going to use grams because in the lab we're going to use grams. So I'm going to use grams. 1 kilogram is 1,000 grams. So 1,000 grams times the change in temperature. What's the change in temperature between -10 and 0? 10. We don't care about the negative. All we want is the change, the difference. The difference is 10 degrees. So I put in 10 degrees Celsius multiplied by the specific heat capacity of ice, not water, ice. Now we all remember what that is. Yes, we do. It's 2.1, okay, joules per gram degrees Celsius. See, we all remembered that. That, if I multiply, will give me how much heat energy it's going to take me to get my ice up to the melting point, step 1. Let's do it. Let's get a number for that. Okay, so let's see. Well, actually, we didn't need a calculator for this one. This is 21, and 21 means 21, even at a college fraternity party. Remember that, 21. 10 times 2.1 is 21, and 21 times 1,000 would be 21,000. So 21,000. The units cancel out: grams, Celsius, joules. So step 1, it'll take me 21,000 joules to get my ice to the point where it's ready to melt. Now I'm going to go write that down over here. So you got to keep room over here. I got room. Am I still in the video here? Okay, I won't write it down yet. I'll do it. Okay, but I'm still staying organized. Step 1 is done. Step 2. Okay, I'm going to calculate the heat it's going to take now to melt the ice. We've got it at the melting point. How much it's going to take to melt it. Okay, so I need the heat of fusion of ice. Remember from the last video? We wrote it down, right? The heat of fusion for ice. It's 333, 1/2 evil, joules per gram. Joules per gram. 333 joules per gram. And we'll multiply that by how many grams of ice do we have? We have 1,000 grams of ice, a kilogram, 1,000 grams. And we'll multiply those. The grams will cancel. And the heat that it takes to melt the ice will be, well, 1,000 times 333, 333,000, 333,000 joules. Now I'm going to circle these, but with dotted circles. When I do dotted circles, that means I found something, I calculated something, but it's not the final answer. So, not the final answer, we just filled in who wants to be a millionaire, okay? So we've done 2 calculations out of the 4. Whew, we're halfway there. Hang in there, people, hang in. Go get some coffee or something, okay? Come on, let's go. Step 3. So this is step 3. Q is equal to mass, 1,000. Now I'm not going to put the units anymore. I put the units in for the first couple to show, do a unit analysis. I save markers, save time, save space. I'm not going to do units at this point once I've shown the units. Okay, 1,000 times change in temperature. 0 to 100. You're going from cold water to boiling water. 100. Change is 100. So 100 times the specific heat capacity of water, which is not 2.1, it's 4.19. 4.19. 4.19, and that would be joules per gram degrees Celsius. Units will cancel, leaving you with joules. So when I get an answer for this, it will be in joules. Okay, so let's see. Let's do the math. So Q equals, well, this, I can do this without a calculator. So this is going to be 100 times 4.19, 419. So 419 plus 3 more zeros is 419,000. 419,000. Okay, so 1,000 times 100 would be 100,000 times 4.1, yeah, 419,000 joules. Okay, all right, so I'm going to give that a dotted circle, meaning I found something that I calculated, but it's not the final answer. And last but not least, step 4. Here's step 4. Okay. Q of vaporization, okay, equals the heat of vaporization. Remember that? Last video. Well, I mean, it was the last video, not 2 videos ago, because the stupid phone call broke my video up. This would have been 1 video. It would have been the last video, but I guess it's 2 videos. Hey, whichever. Okay. Remember? You wrote it down, right? You got it. Okay. 2260. So 2260 joules per gram multiplied by 1,000 grams. And that's going to equal, okay, are you still in my video? Okay, you're running out around, I'm going to move you. Okay. 2,260,000 joules. And we're going to give that a dotted circle. We calculated that for the amount of heat it's going to take to vaporize my water. We have the amount of heat it takes to get the water to the vapor point, the amount of heat it takes to melt, and the amount of heat it takes to get it up to the melting point. So the question was, how much heat does it take to get it from this point to this point? What do we do? You got it. You got it. You got it, Jane. You add those 4 values up and you'll have the answer to this problem. Now wait, before you just click off the video and go, I'm out of here, I'm done, I got it. There's one more thing I'm going to mention at the end of the video. It's important, so stick around, stick around. Add these 4 numbers up and we're going to get the answer. So let's do that. Let's add those 4 numbers up. Okay, 2,260,000 plus 4,190,000 plus 3,330,000 plus 21,000. Boom! All right, 3,033,000. So 3,033,000. We add all of this stuff up. We get 3,033,000 joules. That is the final answer. Final answer, lock it in. Final answer. It takes a little bit more than 3 million joules to vaporize at 100 degrees my block of ice. Yeah. Okay, here's a couple things I want to point out, though. Check it out. This one here is more than these 3 combined. We took this heat, and this heat, and add it. We don't get this heat. This is almost 2/3. Yeah, it's 2/3. 2/3 of the total energy to do this one step. Why? Go back to last unit. You know, begins with I, intermolecular forces. Here you are finalizing and getting those intermolecular forces to separate. We're not separating them here. No separation going on here. Here you separate. It takes a lot of energy to do that. This is a lot of energy, people. That's also why hurricanes become so energetic and dangerous. What does this have to do with hurricanes? Because what happens is when water from the warm ocean rises up with water vapor, goes into the upper atmosphere, when it cools, it condenses. That's the opposite of boiling. This is the amount of energy you have to pump into water to boil it. If you do the opposite, the water goes up from a vapor to a water condensation, which is the opposite of boiling, condenses, you release this energy. That is a truck ton of energy coming out of the condensing water. And there's a lot of water that goes into making a hurricane. And all this energy gets released into the hurricane and makes it a very energetic, volatile system because there's so much energy that's released in the condensation of water. Also, one more important thing that reminds me, and I told you, you're going to want to stick around for this because there might be like a little question on this one. Might be a question. Here it is. Why is it that a steam burn at 100 degrees causes more damage to the skin than if you were to stick your hand in boiling water at 100 degrees? Now, don't try this at home, okay? I'm not advocating. I'm not saying you should go and do this at home. You do this, I get blamed for it, okay? Don't do this. Leave it for the professionals, okay? Let me do it. Think about it. Why would a steam burn at 100 be worse than water burn at 100, boiling water? You stick your hand in boiling water, it's not going to be good for you, okay? Not a good day. 100 degree steam, worse. But same temperature. Shouldn't matter. Yeah, it does. Here's why. That water vapor is at 100 degrees. That's hot, just like the water at 100 degrees is hot. Same temperature. But when that vapor hits your skin is relatively cool. So that vapor will condense on your skin. Boom. Same thing as the hurricanes. What happens is when that vapor condenses onto your skin, it releases all of that energy. And guess where most of that energy is going to go? Into your skin. It's a double whammy. Double whammy. You get the high temperature of 100 degrees. You also get the extra energy coming out in your skin as that water vaporizes on your skin. That is a double whammy, folks, and that is a bad day for you. All right, so, okay, I don't want this to be a really bad day for you, so I'll stop this video, and that is our first problem that we have for this course, and you will have to know how to do that one. Trust me, you.